Oh, sorry. If you're following along in the lecture slides, we're on inheritance number 2. And we're actually 10 slides in because the 2 decks of slides overlap a little bit. All right, so we're talking about inheritance. We've implemented a counter. We've changed the counter class so that you can use it for inheritance. And then we implemented some subclasses. Now there's an issue of what happens when you try to compare 2 counters for equality. So we can compare 2 counter objects for equality. You can compare 2 stopping counters for equality. The question is can you compare different kinds of counters for equality? So can I compare a counter to a stopping counter or a throwing counter to a stopping counter? And the answer is, well, it depends on how you implemented equals. Right? And this is why there's 2 different versions of equals. So if you use getClass, which is probably the most commonly advised technique to implement equals, at least in a textbook sense, then yeah.
Just about that, does like the implements operator, does object implement?
Yep.
Or that's what.
So implements is that's when you implement an interface. Extends.
I'm thinking of instance of.
Oh, instance of, yes. Yeah.
Yeah. So that removes the need for having to check if it's null, right?
Yes.
So if get class is more common, is like instance of more tax, is that more taxing then?
No, not particularly. It's not. There's no. You mean is it more expensive in terms? The answer would be probably not. Yeah.
So is it just kind of convention?
Yes. So I guess the reason is that most classes, when you implement them, they're not designed for inheritance. So the default or the conventional thing to do is to use getClass.
Okay.
But you run into a problem when you try to retrofit that class for inheritance, which we'll see in a second. Right? So if you use getClass to implement equals, which is what we did when we had a regular plain old counter, right? We did this. Right? So we checked if the class of this object is different from the class of the incoming object, return false. Right? So in other words, if the 2 objects have different types, even if they're related by inheritance, the answer is false. They're not equal. Right? So if I have 2 counters, C1 and C2, their values are both 0, then equal says they're equal. If I have 2 stopping counters, both their values are 0, then equals says they're equal. But as soon as you mix the types, right? So if C1 is a counter and C2 is a stopping counter, notice that the type on the left-hand side doesn't matter, right? So we'll talk about that in a little bit too. If you ask, is C1 equal to C2? The answer is no, they're not. It's false because, right, inside equals C1, that's this, right? So C1 is a counter object. C2 is the one that you pass in, and it's a stopping counter object. So counter is not equal to stopping counter, and equals returns false. Right. Similarly, if I make a stopping counter and a throwing counter and compare those for equality, even though their values are the same, they're not equals according to equals. Right. And so now you're in a situation where you cannot compare counters for different types of counters for equality. When you're in an inheritance hierarchy, though, it's often the case that you do want to compare different types for equality. Right? So you want to compare 2 subclasses, for example, to see if those instances are equal. Right? And you can, there are conditions under which, there's some conditions you have to follow, but if you use instance of, now this works. So for example, right, we change equals in counter, right, to use instance of. Right? Now instance of returns true, right, if that thing is a counter or if that thing is a subclass of counter. Right? So if obj is a stopping counter or a throwing counter, it doesn't matter. Right? They're still instance of counter. Right? So now we bypass the if statement and now we compare their values. Right? Yep.
Well, I guess following from my question earlier, I was just thinking why wouldn't you always use instance of
So it's often the case where you'll implement a class and you definitely don't want it to be used for in inheritance. So many of the standard library classes, they're marked as being final. Actually, let's look at that. So I don't actually have a slide for that. So you can have what's called a final class. So Java 8 string. Right, so the class string, or does it actually say? Oh, it doesn't actually, oh, here it is. Right, so when you look at the declaration for the class string, it's marked as being final. Final means you cannot extend the class. So it is definitely not being used for inheritance. Right, so in a final class, you would never implement equals using instance of. You would just use getClass, yeah. And it's often the case where you're implementing a class and you have no intentions for it to be used in inheritance. And so in those cases, you would implement equals using instance of. Sorry, using getClass, not instance of. Right. It's interesting to note that so the person who designed the language says that you should, he recommends that you should use instance of. But equals is widely implemented using getClass instead. Yeah.
Instance of.
Yeah.
Like if you do like the stopping counter and the
Yep.
counter, if in stopping counter you introduce a new field,
Yeah.
would that give instance of as true or false?
OK, so this one we're going to have to draw out. So if you ask, is it an instance of a counter, it's still true. Right? So it's still a subclass of counter. Now, the whole point of introducing another field, that introduces another wrinkle, which I'll talk about in just a second. Okay. That was a good question. But yes, there are still subclasses of counter. So they would still, that instance of will still return true. Yeah. OK, so now, if you change equals in counter to use instance of, C1 equals C2 is true. Sorry, wait. Oh, right. So C1 equals C2 is always true, right, if they have the same value. Right? So these are two counters, they're equal. These are two stopping counters, they're equal. Right? That's a counter and that's a stopping counter, now they're equal. That's a stopping counter, that's a throwing counter, now they're equal. Right? And so if you want cross-class comparisons, then you must make sure that equals is implemented using instance of in the superclass. Right? So in counter, it has to be implemented using instance of. Now, your question was actually a really good one. OK, so this is what counter looks like in the superclass, right? This is what equals looks like in counter, right? Now, if you have a subclass, and the subclass introduces a new field, right? So let's, I don't know, imaginary counter, right? That has some sort of new field in it, right? And then in imaginary counter, you decide you want to override equals because you want two imaginary counters to be equal only if their new field is also equal, right? Make sense, right? You introduce a new field, equals changes, right? Because you have to consider this new field in equality. Now you have a bigger problem, right? Does anybody see what the problem is? Yeah.
Like if you try to compare it to a different one that's like the same instance, it will be trying to check for a field that doesn't exist.
So in your cast here,
Oh, you're casting it to it.
you're going to cast the stopping count. You'll cast to your imaginary counter class. So that is actually a problem.
Well, then will it just like default to the new field?
No. So if you try to cast a counter that's not an imaginary counter to an imaginary counter, you'll get a cast class exception. So now you're going to run into an exception being thrown. There's another problem, though. So if you want to try to compare that other field, right? So if you take two, so if you compare a, I need to write this down. Otherwise, it'll be hard to follow. And I probably don't have a marker that's going to work. I started to bring one, but then I lost it. So that wasn't very useful. All right, so try this. So if you make a counter, yeah, you guys can't see that. Let's try to do it this way. Yes, if you have one, that'd be awesome. Thank you very much. OK, so if you make a counter, So its value will be 0. And you make an imaginary counter. And its value is also 0. And now if you write the following, boo equals, so c dot equals I. Okay, so if you write that, then what happens is c is a counter, right, equals I. So that calls the counter version of equals. Right? So the counter version of equals just looks at the value of I. If it's the same as c, then that returns true. Right? Now the problem is what happens when you flip it around? Right? So when you do that, I is an imaginary counter. So it's the imaginary counter version of equals that runs. Right? Inside this method here, c is not. Inside imaginary counter, you're going to write that as obj instance of imaginary counter. Right? C is not an instance of an imaginary counter. It's a superclass object. So instance of now returns false. Right? And now you end up with equals returning false. True, right? So this is the counter version of equals. And this is the imaginary counter version of equals. Thanks. Right? And so what's the problem here? The contract for equals says equals is symmetric. It doesn't matter which order you call, it doesn't matter which order you put the objects in when you call equals. It should always return the same value. And now equals is not symmetric. And so you've broken the contract for equals. So your imaginary counter class is not substitutable for the counter class. And you've got a busted inheritance hierarchy. So you cannot introduce a new field to a subclass object and have equals work. And be able to do cross-class comparisons with equals. Right? It doesn't work in the language. There is a very, very, very complicated way to do it. And if you're interested in it, you can come ask me about it, and I will direct you to where you can find out how to do it. But it is extraordinarily complicated. And no one ever talks about it. But there is a way to do it. You need features of the language that aren't discussed in this course. Okay, so those are all excellent questions. All right, so that's what happens in equals, right? If you want cross-class comparisons, you have to make sure you use instance of in the superclass, right? And then you don't override it in any of the subclasses. All right, now what else? I want to talk about how many types an object actually has in the Java language. Right, so I've already told you that every object, one of its types is also a big O object, right? I've also told you that if you implement an interface, then one of the types of that object is the interface type. So it turns out in Java, objects have more than one type, right? The types of an object include its own type, right? So whatever class it's defined in, all of its ancestor class types, and all of its interface types. So it's possible to have an object that has dozens of different types. Right? So for example, our class point2, right? We didn't say so, but it really extends object. Right? And if we decide to implement comparable, then point2 actually has 3 types. Right? One of its types is point2, its own type. One of its types is its ancestor classes, so that's object. And any interfaces it implements, so that's comparable. Right, so point2 actually has 3 different types. Stopping counter has 4, right? Because stopping counter extends the counter class. Counter extends object, right? So there's object. And our counters implement comparable. right? And so it also has the type comparable counter. String has 5, right? So string extends object, so there's 2. And it implements 3 interfaces, so it has 5 types in total. So the notion that an object can have more than one type is related to this idea called polymorphism. Right? So polymorphism, if you look up the definition in the dictionary, it says that it's the condition of occurring in several different forms. Right? And so Java has what's called subtype polymorphism. Subtypes are substitutable for their ancestor types, right? That's what inheritance means, right? And that means that for that to work, a subclass, one of its types must also be the ancestor type, right? And so because of that fact, because of the fact that the type of an object includes the type of all its ancestor classes, right? That's how the Java language provides polymorphism. Okay, so there's, when you're talking about variables, every variable can have more than one type as well. Right? So when you write something like counter C, right, then what you're saying is that C, the variable C, right, it refers to a counter of some kind. Right? And so the declared type of C is counter. Right? So what can you use C for? Right? So for C, I can store null in C, right, indicating that there is no object. I can store a reference to a counter object, so equals new counter. Or I can store a reference to any subtype of counter, right? So counter C equals new stopping counter, for example. So the declared type of a variable or a field or a parameter, that determines what operations can be performed. So for example, I can store anything in a variable whose type is object. Right? So I can store an array list in that variable object. Right? Using obj, right? So what methods can I use by using the variable obj? The only methods I can use are those that belong to the declared type. Right? So the only methods I can call with obj are those that are defined in big O object. So for example, I can call toString using obj, but I can't call any of the array list methods using obj. Right? So if I try to write obj.add hello, the compiler will flag that as an error. Right? And this is why in equals, right, equals, its parameter is always an object. Right? It's always a variable of type big O object. Right? And that's why we need the cast inside of the method to convert it to the appropriate type. Right? Because as far as the compiler is concerned, obj is just an object. Right? It doesn't care that it's actually an array list. Right? So here's another example. So if I have a set T, right, and I store a tree set in that set, in the variable T, right, I can call any set method. So I can call add, and that works just fine. Right? If I try to call a tree set method, though, like first, right, again, the compiler flags that as an error. Right? It says that T, there is no method called first in set. Right? There is one in tree set, but there isn't one in set. Right? The declared type determines, the declared type determines what methods can be called using that variable. What's this one? Tree set actually implements this interface called sorted set. Right? So sorted sets are the sets that are sorted. So all sorted sets have a first method. And so this one works fine. OK, now what about the type on the right-hand side? Because on the right-hand side, we know that we can store an object that's a subtype of the declared type. Right? So in C, I can store a stopping counter. So in an initialization statement or in an assignment statement, the thing on the right is the runtime or actual type of the object. Right? So C, its declared type is counter, but its actual type is stopping counter. Right? Actual type or runtime type. So declared comes from the fact that the compiler knows the type of the counter of C, right? It knows that it's counter, right? At runtime, it's possible to write a program where you don't, the compiler doesn't know what the type of the right-hand side of the runtime type of the object is, right? So for example, you can have a little if statement in here that makes a random value, and then based on the random value stores either a stopping counter or a regular counter in C, right? The compiler can't tell which one it is, right? And so only the runtime system can determine what the actual type is, right? So the runtime system is the Java virtual machine. The runtime type determines which version of a non-static method gets called when you use that variable, right? So non-static method, right? Static methods, it's always the class type that determines it's always the class type that determines what method is called. With a non-static method, it's the runtime type that determines it, right? So my declare type is object. The actual or runtime type is counter. So if I use obj to call toString, the version of toString that I get is the runtime type, right? So it's the counter version of toString. So consider the following method, right? So I've got a method print, right? It takes in a reference to an object. How do you print it? Well, you just call toString on the object, and then you print the string, right? The runtime type of obj determines what version of toString you get. So for example, if I print the string s, right, then I get the string version of toString. If I make a list t and print the list t, I get the array list version of toString, right? And if I make a date and print the date, I get the date version of toString, right? It doesn't matter, right? Notice date is declared as object over here, right? It doesn't matter that the declared type is object. When it actually gets printed, it's the runtime type that's used to print the object, right? So declared types determine what methods can you call. The runtime type determines which version of the method actually gets run. Right? And so which version of the method actually gets run is called dynamic dispatch, right? It's called dynamic because it happens at runtime, right? Dispatch is just the word that's used to figure out which version of the method actually gets called. Right? So the compiler back here, right? Your compiler will compile that class no problem, right? It says, okay, there's a method, there's an object of type, there's a obj is a big O object, right? Big O object has a toString method, so this is fine, right? So your compiler happily compiles that, right? It's not until runtime here, right, where the actual version of toString gets called, right? So the compiler can't determine which version of toString gets called, right? There's no way for the compiler to know, right? The thing that knows which version of the method to call is the virtual machine, right? So the version of the toString that gets called can't be determined until runtime, right? And that's why it's called dynamic dispatch or late binding. Dispatch and binding mean the same thing, right? Which version of the method gets called. Dynamic at runtime, late as opposed to early. So early means compile time, late means runtime. Right? So if you ever see the phrase like dynamic or late, it always means runtime. It usually means runtime. Right? So that example there is a really powerful example of simple but really powerful example of polymorphism, right? The whole idea that objects have multiple types means the programmer can write a method using the contracts of the ancestor type, right? And that method will work for objects of any descendant type. Right? So for example, in collections, in collections, so that's Java util. Right? Inside the collections class, so this is the utility class that has a bunch of methods that operate on sets and lists. Right? So for example, add all, right, takes in a collection, C, right, and 0 or more elements, right, and it adds all of these elements to that collection, right. Notice that it doesn't matter what type of collection you have, right. You can have a set, you can have any kind of set, you can have any kind of list, and this method still works, right. Now imagine how this method is implemented, right. So T is just an array of elements, so that's what the dot 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 means, right. So you can imagine that's just an array of elements. How would you implement this method? Well, you just loop over the array, right? And then you would take each element of the array, and you would call add on your collection, right? Why does that work? Because every collection has an add method, right? So it doesn't matter if it's a list or a set, right? You can implement the method add all, right? Just by looking at what a collection has. Right? Collection has add, I can call add, right? And it's guaranteed to work as long as whoever is implementing the methods makes sure that their classes are substitutable or respect the contracts in the collection interface. Where'd it go? Oh, sorry. Okay, so now we're on the inheritance part 3. If you're following along in the lecture slides. Okay, what makes this all work is this thing called Liskov substitutability. Right? And so there's something called the Liskov substitution principle, which is I guess it's a rule that came out of software engineering. The person who came up with this rule, Dr. Barbara Liskov, right here. So she's a Turing Award winner. So basically, what's the equivalent of the Nobel Prize in computing science. One of her contributions, she has many contributions to software engineering and computer language theory. One of them is probably the one she's best known for, is Liskov substitutability. Right? So there is a formal definition of this. There's a mathematical definition for this. I don't care about the mathematical definition, right? What this principle basically says is that a subclass object must behave the same as objects of their supertype, right? Not just the immediate supertype, but all of the supertypes, right? In order to ensure that your subtype objects are really substitutable for your supertype objects requires that the programmer pay very careful attention when they override methods in the subclasses. Right? The language doesn't care, right? No programming language that I know of actually looks to enforce Liskov substitutability, right? So Java doesn't care if you subclass another object, a type class, sorry, and it's no longer substitutable for the supertype, right? The compiler doesn't care, the language doesn't care, the virtual machine doesn't care, right? The people who care are the programmers that are using your classes. If you ensure Liskov substitutability, though, then what that lets you do is that you can write code according to the contracts of a superclass. That exact same code works correctly for any subclass object, right? And that's a very powerful thing. That's a very powerful thing to have. Okay, so what do you have to do to ensure that Liskov substitutability holds? It turns out there's quite a bit. So number one, suppose your class has some invariants. Right? Remember what an invariant is, right? So an invariant of a class means that it's a condition that's always true for objects of that type. So if your superclass has class invariants, then guess what? All of your subclasses have those same invariants. Not necessarily the exact same invariants, but they have to be substitutable for the superclass invariants. Right? So invariants are considered to be public features of a class, and they are inherited. Right? The language, again, doesn't enforce it. Right? But if your class has invariants, then your superclasses also have compatible invariants. Right? So if your subclass fails to support the invariants of its ancestor classes, what does that mean? Or what's the implication? Right? The implication is that code that somebody else wrote can break when you pass it one of your objects. Right? So for example, right, counter has an invariant, right? Counter says that its value is always non-negative. So someone can come along, write a method called isOdd, right? That takes in a counter object, right? The implementation of isOdd is not good, but it's technically correct according to the contract of counter, right? Counter says my value is always 0 or positive, right? So if you take a 0 or positive number, divide it by 2 and look at the remainder, right? If the remainder is 1, it's odd, right? And so this method is correct, and it's provably correct for the counter class, right? So given the contract of counter, this method is provably correct, right? It's mathematically correct. This will pass every unit, oops, sorry. This will pass every unit test that you could possibly write using counter. Right? Now, suppose someone comes along and they make a class, a subclass of counter called descending counter. Right? And descending counter no longer supports the class invariant that the value is always positive or 0. Right? So now descending counter can count down to min value, right, which is negative. Right? It's not hard to do, right? So, and nothing in the language will stop you from doing it. Extend counter, advance is just this value minus minus. That's it, you're done. This will compile, it'll run just fine. Until you pass a descending counter to isOdd, right? So when you pass a descending counter to isOdd, right, descending counter is substitutable for counter, right? So you can pass a descending counter into this method, right? If the value is negative, then say -1 divided by 2, compute the remainder is -1. So as far as this method is concerned, right, a counter whose value is -1 is not odd, right? It's even, which is wrong, right? The method is correct, right? It's the subclass that's incorrect, right? And so now you've written a class that breaks somebody else's code, which is not good, right? That's not something you want to do, right? The correct solution here, so there's two things. Number one, someone shouldn't have written the descending counter class. Number two, you shouldn't write isOdd this way, right? If you want to check if a number is not odd, is odd or even, it's always not equal to 0, right? Or alternatively, test if it's even, because then it's always equal to 0, right? The remainder after dividing by 2. So that's not a great way to implement isOdd, but technically correct. Okay, so if your superclass has invariants, that doesn't mean that the subclasses have the exact same invariants, right? So the subclasses can modify the invariants as long as the superclass invariants are still respected, right? So for example, I can make a range counter class, right? And a range counter counts between a range of non-negative values, right? So I can make a range counter that counts between 5 and 10, for example, right? So I can change the invariant now, right? So a range counter, it has the invariant that the value is always between min and max, right? That's a different invariant than the superclass has, right? The superclass says the value of the counter is always 0 or greater, right? And now I'm between min and max, but that's fine, right? If the value is between min and max are both positive, right, that still satisfies the superclass invariant, right? So this is fine. So you can, in fact, change the invariants, but if you change the invariants, they have to still satisfy the superclass invariant. All right. So for the rest of this lecture, I'm going to introduce this class called shape. Right, so if you want to see the full implementation of the shape class, you can look in the substitutability notebook. Otherwise, I'm just going to tell you enough about the class for the purposes of the lecture. Right. OK, so shape is what's called an abstract superclass for all 2D shapes. Right. So an abstract class is a class where you cannot use it to make objects directly. Right. So in this case, I cannot make a shape object directly, right? So in other words, I can't write new shape and have it, or somebody who's using the shape class can't write new shape. Right? And you might say, well, what's the point of making this class if we can't make a new shape? Right? So the purpose of an abstract class is to serve as a superclass in an inheritance hierarchy. Right? So in your superclass, you declare all the methods that are common to all shapes, right? And you declare all of the fields that are common to all shapes. Right? And so what the abstract superclass lets you do is it gives you the building block of all shapes. Right? If someone wants a shape object, they subclass shape. They get all of those methods, and they get all of those fields from the superclass. Right? But you can't make a shape. Right? You can make a square or a circle or something else that that extends shape. Right? But you can't make just a plain old shape. So an abstract class, its name is always written in italics in a UML class diagram. So if you're ever looking at a UML class diagram and you see something in italics, that's indicating that it's an abstract class. So here's a partial implementation of shape. Right? So we mark it as abstract. Right? As soon as you mark it as abstract, the compiler will prevent people from making shape objects. Right? We're going to say that all 2D shapes have an independent width and height. Right? So that's important, independent width and height. Right? Furthermore, the width and height have a minimum value of 1 and a maximum value of 100 units. Right? So every shape has a finite, non-zero finite size that's between 1 and 100. Right? And so there are the minimum and maximum lengths. Right? There's our width and height of every shape. They're protected, so the subclasses have access to them. Then there's a bunch of constructors and some methods that aren't shown here. Right? One of the methods, though, is width. Right? So width returns the width of this shape. Right? It promises to respect the class invariant. Right? So the returned width is always between 1 and 100. And finally, there's one more method that I want to talk about. So there's something called area upper bound. So area upper bound returns an upper bound on the area of the shape. Right? Now, if you have some complicated shape, so some squiggly outline of an object, right, it's hard to compute the exact area of that shape. Right? So instead, what this method does is it computes an upper bound on the area. Right? So it estimates the area, overestimates the area, actually. So it guarantees that whatever area is returned by this method is equal to or greater than the true area of the shape. Right? So for a generic shape, its upper bound is just the width times the height. Right? So it's the full rectangle containing that bounds the size of the object. Right? Now notice what the contract says. It says subclasses should override this method if they can provide a tighter upper bound. Right? So if you have a circle, you should return pi r. Well, you should return, sorry, not a circle. If you have a triangle, right, you should return the height of the triangle times the width divided by 2. Right? And that's the exact area. Finally, set dimensions. So set dimensions changes the shape so that its width and height are the given width and height. It checks the width and height to make sure that the size of the shape is valid. Right? So again, it makes sure that the class invariants are always respected. Right? And remember again, shapes have independent widths and heights. Right? And so this one guarantees that it changes the width to that and the height to that. All right. So as soon as you have the shape class, you can start to write methods using the shape class. Right? Even though you can't make a shape object. Right? So you can write a method that randomly changes the size of a shape. Right? And furthermore, this method will be provably correct. Right? It will pass every possible valid unit test that you can write using the shape class. So here's a method that randomly changes the size of a shape. Right? So it takes the current width of the shape, and then all this does is it scales it by a small amount, up or down. Right? So it changes the size of the shape by less than 1%. Same with the height. Right? It then makes sure that W and H are both valid widths and heights, right? So between 1 and 100. Right? If they're valid widths and heights, it changes the dimensions. Right? If not, then it just leaves the shape the size that it is. Right? Where's our, okay. Okay, so this method here is correct, right? It does in fact change the size of the shape if it can. If it can't, it doesn't change the size of the shape, right? But it does randomly change the size. Okay, suppose we cook up now we need an actual class that extends shape, right? So we can do rectangle, right? And similarly, you might consider doing square. So this is again the circle ellipse problem, right? Here we're going to try to extend rectangle using square, right? Square is just a rectangle whose width and height are the same. We already know that's going to be a problem, right? Because the shape class itself said that all shapes have independent width and height. All right, so many methods place restrictions on their parameter values, right? So remember, methods have preconditions, right? Set dimensions has the precondition that the width and height must be between 1 and 100. If a subclass overrides a method, then it must accept all of the parameter values that are accepted by its ancestor classes, right? So if a subclass overrides a method, right, then whatever values you could call that method with in the superclass, you have to be able to call that method in the subclass as well. You have to be able to use those values to call the subclass method as well, right? So if you really want to try to force square into this hierarchy, right, what does set dimensions look like for square? Right, so for example, you could try to throw an exception if the width and height are not equal. Right? So in square, we can extend rectangle. Right? In set dimensions, right, I can impose the extra precondition that the width and height must be the same. Right? I've added an extra constraint. Right? If that constraint's not true, we throw an exception. Right? Otherwise, we just change the width and height of the shape. Right? Now notice, to change the width and height of the shape, I could write this width equals width, this height equals height, or you can call the superclass version of set dimensions. Right? So if you want to call, if you're overriding a method, so here we're overriding set dimensions, and you want to call the superclass version of the method, you can do so. Right? You just use super in front of the method name. Right? So this calls the rectangle version of set dimensions, which goes ahead and sets the width and height. Right? What's the problem of adding this extra constraint? Right? Go back and look at random scale. Right? So in random scale, right, we've already concluded that the method is correct the way it's written. Right? Until you pass in a square. Right? Because as soon as you pass in a square, the width and height get changed to some random value. And it's almost certainly the case it's not the same random value. Right? And so when you call set dimensions, suddenly random scale throws an exception, which it shouldn't. Because, oh, I don't have it here. Because random scale doesn't throw an exception. Right? It put in a condition here explicitly to prevent an exception from being thrown. Right? But now it throws an exception. So someone's code, whoever wrote random scale, right, that was written using the superclass contracts, now breaks when you pass it a subclass object. Right? So whoever wrote the square class just managed to break someone else's method. Right? So you cannot add an extra precondition or extra preconditions on a method. Oh, so this is just an aside. Right? So when you're overriding a method, it's often the case where you'll realize, hey, the superclass method does a lot of the stuff that I need to do. Right? So if you want to call the superclass version of the method, just put the super keyword in front. Right? The Java language is normally pretty good about recycling keywords. The exception is with super and this. They mean different things in different contexts. Okay, so let's stop there, and we'll continue this discussion on Tuesday. Right? Any questions, I guess, on today's lecture? All right, so have a good weekend, everybody, and I will see you.